Okay, so we're going to talk again about enzymes here. Um, so we're going to go a little bit more into detail, ending up talking about enzyme inhibitors. And this will lead us nicely into antibiotics and antiviral drugs. So again, we can be talking about topical um, topics. Okay, so just to remind you from last time, enzymes are proteins that catalyze reactions in a biological system. And so they can have molecular masses, like it says, it can have molecular masses of several million daltons. And dalton, just to remind you, that's an atom. So they can be made up of several million atoms, but they can catalyze reactions on molecules that only have two or three atoms, like CO2 and dinitrogen. Carbonic anhydrase is a good enzyme, and it can catalyze the reaction of a million molecules of CO2 a second. And so, what the reason that in this case carbonic anhydrase is so um, fast and is an awesome enzyme is because this is one of the main ways that your body controls pH in your blood. And that is going on all the time because your body is recognizing the amount of CO2 um, in your blood, that pH that's related to the amount of CO2 dissolved in your blood, and that's what's telling you when that you need to inhale and exhale. So carbonic anhydrase has to be really good because that pH is basically how you know to breathe. So that's really important, and that's why it's such an awesome enzyme. So, just like we talked before about drug receptor complexes, and so, like we were saying last time, completely analogous to this is enzyme substrate complexes. So, what the enzyme does is it recognizes a substrate and it catalyzes a reaction with it. So, different than what we talked about with drug receptor complexes, the enzyme is going to change its substrate, right? It's going to make a chemical reaction on the substrate, and um, that's what we're looking at with enzymes. So enzymes work again by they work by raising ground state energies, but they mainly function by lowering transition state um, energies, and we talked about this last time. And Linus Pauling designed it in an enzyme or defined an enzyme as this flexible substrate template. And we talked again about last time about Daniel Koshland, or we talked a couple times about Koshland and his induced fit hypothesis with how enzymes. But the key thing to take away from this slide is really what's in blue there, which is that enzymes stabilize transition states. And we talked before about how enzymes are a kinetic thing, they don't affect the thermodynamics of the reaction. They affect the kinetics of the reaction. And the way that they affect the kinetics of the reaction is by lowering the activation energy, by stabilizing the transition state. So, just like when we talked before about receptors, remember that we had that receptor binding region, and we talked again about this last time, is that so the substrate binds a small part of the enzyme. And again, this is a hydrophobic pocket, just like when we were talking about receptors. Again, this is a hydrophobic pocket. And that hydrophobic pocket typically is called the active site. So the two key factors are specificity and rate acceleration. So rate acceleration, we just mentioned, that's that transition state stabilization. But specificity, this is how good an enzyme is at recognizing its substrate. So how good an enzyme is at recognizing its substrate, that's its specificity. And the way that it does that is typically through non-covalent bonds. Those non-covalent bonds that we've been talking about when we talk about drug receptor interactions, the same things, those same bonding modalities are being used by the enzyme when it recognizes its substrate. So another thing is that enzymes require cofactors. So we've talked very briefly about this when we were talking about statins and learning about SAR, but we'll talk about this a lot more in detail. And these cofactors or coenzymes are going to be organic molecules and metal ions. And these are going to be a lot of what's in vitamins that you take or the vitamins in your food. What these vitamins are cofactors. We'll talk more about this. These molecules that the enzyme needs in order to act as a catalyst that you need to eat to provide to those enzymes in your body. So we're going to talk now about specificity of binding and specificity of reaction. So the maximum binding, this number right here is just to give you, is a descriptive number. I don't want you memorizing this number. And so basically, enzymes can be very specific in that they can be they can have absolutely just one substrate, or they can be have many substrates. These are also known as promiscuous enzymes. And remember, all enzymes are chiral. All enzymes are chiral because they're all made up of chiral amino acids. And so all amino acids are L, and typically the stereocenter is S. There's a couple, or not a couple, there's one amino acid, cysteine, right? That's technically R because of how you would number it based on the sulfur, but it still would rotate plane polarized light in the same direction as the other amino acids, so they're all L amino acids. And this means that enzymes are going to possibly, not always, possibly recognize enantiomers differently, and recognize diastereomers differently, and act on enantiomers to give diastereomeric products. Again, this is not a rule necessarily. It depends on the enzyme. So even though all enzymes are chiral, how they interact with chiral substrates depends on the specific interactions between the substrate and the enzyme. So the binding energy can be different with one enantiomer, not the other. So basically what can happen is that both enantiomers can form enzyme substrate complexes, but only one is converted to products. And so the other one, and when something's converted to a product, that's called turnover. So when a substrate is converted to the product, the enzyme substrate complex goes to the enzyme product complex. That's known as turnover. And if something binds the enzyme, a substrate binds the enzyme, or potential substrate, I should say, binds the enzyme, and there's no reaction, but it does bind, that's called non-productive binding. So the specificity of the reaction, so this is reminding you before, is that it's going to depend on the groups in these key molecular interacting groups in the active site, these key side chains in the active site. It's also going to depend on cofactors. So there's metal ions or organic molecules in the active site. So the way that this works is that basically an enzyme can have a group that only HA is removed specifically.